let's get started. So next Tuesday, you've got a homework assignment due, and we won't be meeting here in class. I'm going to be down in Clemson working on the FE exam, and so your lecture that day will just be a recording. I'll email the link to you, and it'll also be posted on MU Online. So I won't actually see you again until next Thursday, but you'll still be able to turn in your homework assignment, and there will still be class. It's just you can watch it in your pajamas that day, I guess. Today we're going to focus on talking about Bernoulli's equation. Before we do that, are there any questions about these announcements or anything from yesterday's lab? All right. So Bernoulli's equation is going to be a new way for us to look at how pressure changes when water is moving. Remember, the hydrostatic equation told us pressure changes just simply as a function of depth. And Euler's equation told us what happens to pressure when there's local acceleration, meaning that the velocity is changing with respect to time. Bernoulli's equation we're going to use when there is convective acceleration, and it'll tell us what kind of pressure changes we can expect to see in cases of non-uniform flow. Before we get into that, let me give you a couple of key idea hints on the assignment that's coming up. So one of the problems, problem 46, you have a tank of liquid that you'll notice is not water. So they've specified the specific gravity of this liquid. It looks like it's more dense than water. And it's accelerating to the right at 1 g and down at 2/3 g. So what's g as an amount? 9.81 if we're in SI units, and here we are. Okay, so it's accelerating to the right at 9.81 meters per second squared and down at 2/3 of 9.81 meters per second squared. Now here's how they ask it in the book. And this is really important because they ask you in a weird way that actually makes it tons harder. They ask you to find the difference in pressure between A and C, and they also ask for the difference in pressure between B and C. And why that's confusing is it would be so much easier to find the difference in pressure between C and A if you do B and A first. So you just basically got to swap what order you solve things in compared to what they're asking. So my suggestion is, first of all, apply Euler's direction in the Euler's equation in the z direction. So vertically, between A and B, consider that downward acceleration at 2/3 g. So you're going to expand out Bernoulli's equation, and L, it's some direction. So L is going to be z. And so this delta L becomes the difference in elevation between point 2 and point 1. And remember, we choose what is location 2 by how high it is. And so A is above B. It's got more of the vertical. And so that's going to be our location 2. So you go through the Euler's equation in the vertical plane to find the difference in pressure between B and A. My suggestion is to then, after you've done that part, then apply Euler's equation in the horizontal to find the pressure difference between B and C. Now, they never asked you to find PB minus PC. They didn't ask it directly, but you have to do that in order to find PC minus PA. So in other words, you can't just go straight from A to C. You have to go from A to B and then from B to C in order to find the pressure difference between A and C. So here are the hints. I'm saying you have to, number one, break it up into the two directions. But my suggestion is do the vertical first and then do the horizontal. Combine the two differences, and that will tell you the difference in pressure between A and C. So you're not actually finding the actual absolute pressure at any of these three locations. You're solving Euler's equation just for the differences. So you don't have to know the pressure at any of the locations to find the difference. So we spent part of 2 class periods working on Euler's equation, so I hope that that previous experience coupled with these hints will send you in the right direction for that problem. But if you have any problems when you're working on it, please let me know. Question?
So when it says accelerating downward at 2/3 g, that's already including g into it, correct?
Euler's equation includes g into it. Let's look at how we develop Euler's equation in the vertical direction. So it is, we're going to say P2 plus gamma z2 minus P1 minus gamma z1 is equal to minus delta z times the density and the acceleration in the z direction. Okay, so the acceleration that you put in for z, you're going to put a minus sign because it's down, and then 2/3 times 9.81 meters per second squared. So that's the quantity that you'll put in for the acceleration in z. Now the effects of gravity is already accounted for over here. You know, over here is where the hydrostatic effects are kind of accounted for. On the right side of the equation is where that external acceleration is handled. So P2 minus P1, you just move everything else to the right-hand side of the equation, and then it'll simultaneously account for the downward acceleration and then the effects of gravity. Are there other questions about this one?
I got a question. So from B to C,
Mm-hmm.
we said in the right-hand direction is your 1 to 2.
That's right.
So C being 1, B being 2?
Yes.
Okay.
Yep. So he's remembering that not only do we have some convention for vertical, but also there's convention for 1 versus 2 in the horizontal direction. And whatever is further to the right is what we're calling location 2. So why are we bothering with 2 versus 1? Well, you know, if an acceleration is going to be positive versus negative, then we have to keep track of what point is further to the right versus what point is further to the left. Because remember, the general rule is pressures increase in the opposite direction of acceleration. I've repeated that phrase several times, and the reason why I've repeated that phrase is so that mentally you can do a double check and say, well, if this is accelerating to the right, then we should expect pressure C should be larger than pressure B. So you have kind of like that qualitative expectation that when you're crunching the numbers, you find a pressure increase where pressure C is bigger than B. So the equation itself has some places where, for example, Z's are going to be relative to some elevation datum. And then also the acceleration has a direction component to it. So it's important for us to not use 2 and 1 interchangeably in Euler's equation. Great questions. You got another one?
So when you start one of these problems, you basically just put your x and y axis wherever.
What do you mean?
Like for this, I think I would put it at c.
Oh, you mean the datum?
Yeah.
Yeah, I'd do the same thing. I'd say my vertical datum is at C. But you're right. Your numbers, when you're finding Z1 and Z2, you could have said, let's have the vertical datum be at the top of this tank. So when I'm working vertically, I could say ZA is 0 and ZB is -3. And you'd still get the same numbers that way. Yeah. Any other questions? All right. Bernoulli's equation. Euler's equation was all about local acceleration. Local acceleration is corresponding to changes in velocity over time. And what we learned about, we had a physical example of it yesterday with the blue dye. You know, I emptied it successfully. You'll notice I'm not covered in blue. I don't have any more blue on my hands because I had to fill up that blue dye all the way to the top to get enough pressure to force it through that needle. Okay, so when I took it out, I was walking very slowly to the sink before I poured it back into that jar. And why was I walking slowly? Because any local acceleration would cause that liquid to slosh. Remember? We looked at some of that. We looked at the water sloshing from side to side. So maybe I should change this example to how deeply can you fill the blue ink? And I only had about 2 millimeters. So it took me a few minutes to walk over towards the sink, but I did it. So Euler's equation, the point is it predicts not only changes in pressure, but also changes in the liquid elevation. And so it was the piezometric pressure that we're looking at changes in the piezometric pressure due to local acceleration in some L direction. So whereas we've already done that, we know there's other types of acceleration. We have to have some other formula to handle convective acceleration, which is changes in velocity with respect to position. So Bernoulli's is kind of like the different version of Euler's. Euler's is for local, Bernoulli's is for convective. Euler's was for changes in velocity over time. Bernoulli's is for changes in pressure, how pressure and elevation change when velocity changes over position. So here is Bernoulli's equation. It's a little bit more straightforward to apply. People generally tend to understand Bernoulli's a lot quicker than Euler's. And the other thing that's kind of nice about Bernoulli's is we don't have to be so picky about what is location 1 and what is location 2. That's kind of more or less interchangeable in Bernoulli's equation. But what Bernoulli's equation says is that when you have flow between 2 points, that the pressure head, the elevation head, and the velocity head is going to be constant between those 2 points. And so let's look at each one of these 3 terms. P1 divided by gamma, if we consider the units of that, remember P1 is units of newtons per meter squared, and then gamma is going to be newtons per meter cubed. And so overall, the units of this is going to be meters. You know, because it's going to cancel out the newtons, cancel out the meters squared. So all we're left with is meters in the denominator of a denominator. So that goes up to the numerator. So we've got units of meters for the pressure head, which is lucky because we want to add it with z, which is some distance, an elevation. It will also have units of meters. And then we're going to add it to this third term is called velocity head. And so let's look at the units of velocity head. We have meters per second for velocity, which we square, and then it's divided by g, which is meters per second squared. And so the second squareds will cancel out. We'll have meters squared divided by meters, so that leaves us with meters as the units for velocity head. So each one of these terms can be added directly, but what we're saying is as water flows through some field between 2 points, there is conservation in the sum of those 3 terms. The Bernoulli's equation is the application of Euler's equation to steady flow, and then there are some conditions. It can only be applied in a very narrow range of circumstances. Bernoulli's equation only really applies when you have steady flow along a streamline for incompressible, inviscid fluid. So let's break that down into all 4 of the components. Now, steady flow, you know well enough what that means. It means that the velocity is not changing with respect to time. It's only changing with respect to position. So we have some sort of a fitting, like maybe it's a nozzle, where there's been something that's causing a change in velocity with respect to position. In this narrow diameter section, the velocity is going pretty fast because it's a small diameter pipe, and we've got this much larger cross-sectional area where the velocity is slower, and so I made the arrow a little bit shorter. So what we're saying is that Bernoulli's equation has to be steady, so the flow conditions aren't changing over time, they're just changing as a function of position. Now along a streamline, so what would the streamlines look like? Well, the flow that's over here is going to move there. Our streamlines are basically an indication of the relative direction of the velocity at any location in the field. So we've got our streamlines that are just kind of indicating the direction, and these non-parallel streamlines means, oh, there's some acceleration happening there, there's a change in velocity. Now, these last 2 points, well, wait, along a streamline. So what it means is that location 1, here's location 1, and here's location 2. They're on the same streamline. Bernoulli's equation couldn't be used to predict how the pressure is changing, for example, here versus here. We couldn't do from the top of the inlet to the bottom of the outlet because those are different streamlines. If we tried to predict the pressure change, we'd have some inaccuracies. So it's not that Bernoulli's equation would be like completely wrong, but it wouldn't be as accurate if instead, if we were trying to predict the pressure along a streamline. Okay. So does that make sense so far? The first 2 restrictions, steady flow and along a streamline. Is everybody with me there? Okay. Now, these last 2 is where things get really interesting, because what we're saying is we really only ought to apply Bernoulli's equation if the liquid in question is incompressible. So what kind of fluids are incompressible? Because remember, there's gases and there are liquids. Both of those are fluids. So fluid is the more broad term. Fluid mechanics includes gases and liquids. And so between gases and liquids, which are incompressible? Liquids. Okay. So we're saying, all right, Bernoulli's equation should be used for liquids. Now, inviscid is a word that probably not anybody knows yet, but you're going to learn it today. Inviscid means a fluid with no viscosity. Okay, a fluid with no viscosity. I'm sure you've been poring over the tables in your appendix. Have you found any fluids that have no viscosity? No fluids have no viscosity. But between gases and liquids, which one gets closer to the description of a fluid with no or very little viscosity? What kind of fluids are more viscous, liquids or gases? Liquids. Yeah, think about walking through the pool. The reason why you can only walk slowly through the pool, you can't run through the pool, you're walking slowly because the fluids are deforming at a slow rate as your legs are moving through the water. So the high viscosity is kind of making you apply a big shear force for that deformation, whereas air is easy to walk through because there's less viscosity. There's less resistance to your movement through air. But air still has some viscosity. So the reality is that there's really no fluid that meets the criteria. Because what we're saying is the fluid has to be incompressible. Well, no fluid is perfectly incompressible. Even liquids can kind of be compressed a little bit. But liquids are a little bit better in terms of meeting the standard of incompressibility. But then we're saying also, this Bernoulli's equation should only be applied for fluids that don't have any viscosity. Now, gases are kind of good at that. I mean, they have very little viscosity, but they still have some. But the point is that Bernoulli's equation never really applies. And the reason why is it can't account for frictional losses. So as long as we keep in mind that there are limits to Bernoulli's equation, we can still be successful with it. It's still useful, but it's never going to be perfect. It's never going to perfectly describe what we observe out in the world. And so when we get into the lab and we test Bernoulli's equation, it's not going to be one of those labs where you have 1% error, because Bernoulli's equation, we're going to be using it with water, and water has viscosity. And so one of the weaknesses of Bernoulli's equation is it doesn't account for friction losses. And that's why this whole discussion of, that's what this whole discussion of viscosity is all about. A fluid that was inviscid wouldn't experience any friction losses between location 1 and location 2. There would be a pressure change due to the expansion in the pipe, but there wouldn't be any pressure change due to friction or due to energy loss through the friction. So we'll revisit those assumptions, but you need to commit those 4 assumptions to memory. Any questions before we move on? Let's briefly talk about what models are in engineering terms. A model is some sort of a representation of a system, and Bernoulli's equation is an example of a model. It's a formula that we says will describe what we observe in reality, as long as certain conditions are met. So other types of models may be like an aircraft model that goes into a wind tunnel. And we use this small-scale model to predict the performance of a prototype, where it's a lot cheaper to make changes and do experiments to the model than it would be to do the same kinds of experiments and tests on a prototype. So models give us the ability to predict what's going to happen in the real world. So Bernoulli's equation could be thought of as an engineering model. It's a model that predicts how changes in pressure, elevation, and velocity occur between 2 points. So here's another model. Like this formula could be used to predict the range of an airplane. And you'll notice that the difference between Bernoulli's equation and this other model that's here is Bernoulli's equation is a fundamental equation. It's based in the laws of science, whereas this empirical equation is just based in observation. And it's kind of like, it's got all these factors in here, 4.37, 0.043. You know, these are just probably curve fitting factors where there was a lot of observed data and they're trying to do a best fit equation for some graph, you know, and you've probably done the same thing in Excel before where you have a bunch of scattered data and then you try and make a curve that basically fits the data as good as you can, and you can tell Excel, give me an equation there, y equals mx plus b, and it does its best to make some sort of an equation. I guess it wouldn't be that for a curve, but you can use a statistical approach to minimize the difference between the curve and the observed data, and you end up with some formula. So empirical equations we should generally feel more comfortable using than these. I'm sorry, fundamental equations are maybe given greater weight than empirical equations because they are based in like the laws of the universe. Now, when we apply these models, there's some terminology that the book goes into talking about the boundary is it defines the extent of the system. And so when we're going to be doing some work in the lab, we will have to have the boundary be, like in the case of Bernoulli's equation, it will be a pipe that's changing in diameter. So inside some control volume will be the boundary of our system. And the variables in a model would be the elements of the system that can change. And so you'll see here that the variables in Bernoulli's equation are pressure, elevation, velocity. But then there are some constants that don't change. So the parameters in a model would be the unit weight of the fluid, as long as we're talking about a constant temperature, gravitational acceleration, as long as we're talking about the same planet at roughly the same elevation, because gravity does vary slightly over the surface of the Earth. But I just wanted to, since we're talking about Bernoulli's equation, which is a model for predicting pressure change, I thought I'd tie it into the things that are discussed in the book in terms of engineering and models. Okay, so what Bernoulli's equation says is that for steady flow with an incompressible fluid that has no viscosity along a streamline, the sum of the piezometric pressure and the kinetic pressure are constant. Now this is another way of looking at Bernoulli's equation. What I showed you before, the first time we looked at it, all of the units were in terms of meters, because we had pressure head, elevation head, and velocity head. And each one of them, when combined, was in terms of meters. Now here, each of the terms is going to be in terms of newtons per meter squared. And that's the units of pressure. What about gamma z? So gamma times z. So gamma is newtons per meter cubed, and then we multiply that by meters. So that is also newtons per meter squared. So we can combine pressure and gamma z. And then there's this other term called kinetic pressure. Let's look at what are the units of kinetic pressure, where it's density times velocity squared divided by 2. So the units of density would be kilograms per cubic meter. The units of velocity are meters per second. And then we're going to square each term. So we've got meter squared and second squared. All right, now remember that a newton is a kilogram meter per second squared. So we've got those in here. We've got kilogram, meter, and second squared. So I'm going to translate this. I'm going to say we've got newtons, so that cancels out this kilogram, cancels out the second squared, and it uses up one of our meters in this meter squared. So we've got newton, meter, and then divided by meter cubed. So what we're left with is newton per meter squared. So that just kind of shows that the kinetic pressure can be added to the piezometric pressure, and it's all going to have the same units. So what we're saying is between 2 points, the sum of all of this together, the kinetic pressure combined with the piezometric pressure, is conserved as flow goes between 2 points. And so if we had any kind of a scenario where flow is changing with respect to position, so again, we call that non-uniform flow. If we have non-uniform flow, then along the streamline, there is conservation of piezometric pressure and kinetic pressure. So we can either express Bernoulli's equation in terms of pressure units, or we can write it in terms of length by dividing each of these terms by gamma. So pressure divided by gamma is pressure head. Gamma z divided by gamma just leaves us with z. This velocity term in the kinetic pressure, if you divide that by gamma, then we have density divided by gamma, which is where the g comes from in the denominator. And of course, the velocity squared stays. So between the 2 points, there's conservation in these 3 terms. You remember that we did this example on the whiteboard having to do with convective acceleration. This is the type of scenario where we can use Bernoulli's equation. If we know some change in velocity, we can use it to predict the change in pressure. So let's do that. Let's say that we have some pipe that's changing diameter, and in this illustration, the pipe its diameter is increasing so much that the velocity goes from 5.5 down to 0.6358. So at 1, the pressure was 400 kilopascals. At 2, we don't know the pressure. So what I'd like you to do is calculate what is P2. Now what you'll notice is I've selected location 1 to be the center of the pipe. Location 2 is at the center of the pipe, and so the 2 z's are going to be the same. Z1 equals Z2. So you can just cancel those terms out of Bernoulli's equation. and substitute in the given velocities, substitute in the known pressure of 400 kilopascals, where since this is water, gamma is 9.81 kilonewtons per cubic meter, or you could change kilopascals into pascals. But in any case, what we're trying to do is find P2. All right, so here's the deal. We've got water that's moving fast, and it's transitioning into slower moving water. Now, what we know is there's conservation of energy between the 2 points. You know, energy is in 3 places. Some of the energy is as pressure head. Some of the energy is as elevation. Now, those 2 terms together, we usually think of that as potential energy. Whereas the energy that's tied up as the velocity, that's kinetic energy. So the energy is in 3 spots at location 1. And as the flow changes, the velocity decreased. And so less of the energy is in the kinetic term, which means it has to go somewhere if there's conservation. Now, since it's on the same vertical plane, since Z1 and Z2 are equal, what that means is that the additional energy that used to be as velocity is going to go into an increase in pressure. And so that's why the pressure at location 2 is higher. You know, when we actually crunch the numbers here and find out how did the pressure change. So the 3 terms, the pressure at 2, you'll notice, by the way, I solved it symbolically before I started putting in the numbers, just because I like to see the relative magnitudes of where the energy is. So the pressure at 2 is going to be related to how much pressure there was at 1. Well, where was the energy when the flow was at location 1? Most of the energy was in the pressure head term. You looked at 40.775 meters was because of the 400 kPa that it was saying. A relatively smaller fraction of the energy existed as the velocity head. You know, if we calculate it, it's only about 1.54 meters of energy that's as the velocity head. So there's not that much energy in the velocity head. It gives up most of it because the velocity at location 2 is so much lower, where it's only going 0.6358 meters per second. So that means there's almost no velocity head left at location 2. So this 415 kilopascals, what it says is that the energy just changed form. Most of what was in the velocity head got transferred into additional pressure at location 2. Now, maybe for some of you, these results are a surprise, because if you just look at the picture, maybe some of us look at this picture and we think, well, the flow at 1 was like all confined in a smaller pipe, and then when it gets to 2, it's less confined. So wouldn't the pressure be lower? And you know, I can kind of understand that thinking, but the reality is that it's not about, you know, like the size of the pipe that the water is in that directly affects the pressure, but the pressure is just, it's a form of energy. And so the velocity was faster at 1, and now it's slower at 2. So where's that energy going to go? It's only got one spot. It has to be an increase in pressure. Any questions about this example or the calculations that you went through to get the final answer? Yeah.
If the pressure's higher at 2, wouldn't it push the flow back toward the left?
That's a good question. The answer is no, it wouldn't. And the reason why is that we're assuming that there's no energy lost due to pipe friction, but in reality, like in a real pipe network, so let's say we've got like a long pipe and we observe the water is going from one direction towards another spot. Like, why does the water go from 1 to 2? It's because at 1 the pressure is higher, and at 2 the pressure is lower. Like, water flows downhill. We've all seen that. We know that. But the other way of water flowing from a location of high energy towards a location of low energy is that it flows from locations of high pressure towards low pressure. So in this case, what we have is a pressure increase that's due to just a brief expansion. So let me draw that expansion in the context of the greater pipe. So here's this expansion. All right, so here's 1 and here's 2. Now, it's true that the pressure at location 2 is higher than it was at location 1, but if we look at this extreme end of the pipe compared to this one, there's still going to be friction losses as you go in the direction of flow. And so like in the broader scale, the pressure on the left side of the system is higher than the pressure on the right side of the system. And then the other thing about it is that the water is forced to the right because there's still water on the other side of it that's coming this direction. So the continuity equation, which we talked about a little bit in the lab yesterday, Q equals VA. Since it's an incompressible liquid, it has to still be, for any liter that comes into this transition from the left, it has to exit on the right. So it's an interesting question, why is the water going from left to right if the pressure is higher on the right? It's because we only applied Bernoulli's equation at a couple of points that are relatively close together, because Bernoulli's equation can't handle pipe friction. But in a situation where there is pipe friction, then there's going to be pressure decreasing in the direction of flow, and that's going to determine whether flow is going to the right or to the left, is kind of the pipe friction and where is the energy higher. So, any other questions? All right, well, let's apply Bernoulli's equation in another example here. In this one, we've got a nozzle where the diameter is decreasing, and so the velocity will be increasing inside of the nozzle. And as the nozzle is necking down and the velocity increases, the pressure is going to change as well. So if velocity goes up, what happens to the pressure? It has to decrease. And that's the reverse of what we saw on this one. On this one, the velocity decreased, so the pressure increased. In this one, the velocity increases, so the pressure decreases. Now, they've got kind of a weird setup here to measure the pressure at location 2. They've got this stagnation tube where you'll notice that the tube is pointing at the wind, the air that's moving through this nozzle. And so the air is kind of like dead-ending. It's stagnating at the opening of this tube, and it's causing the pressure to increase in the tube even more than it really would ordinarily if it was just connected sideways at the nozzle. Like if it was connected like this, if we were connecting at this spot, then the pressure wouldn't be quite as high as when you've got the tube pointed like this. Because if the wind is going past the opening, it's just going to be measuring the ambient pressure. But if this gas is running into the tube, then it's going to be measuring the ambient pressure, but then also that wind, like it intercepting the streamline, there's going to be an additional increase in pressure that is associated with the transfer of the kinetic energy into more pressure. So what we're going to do is we're going to apply, in this example, Bernoulli's equation at 3 points. We're going to have location 1, location 2, and then inside the tube. Those will be the 3 spots where we're applying Bernoulli's equation. Let's say that we're told the cross-sectional area at location 1 is half of the cross section. No, area 1 is 2, area 2. Yeah. Okay, it's double. So area 2 is half of the area at area 1. Area 1 is double the area 2. So what that means is that V2 is twice the velocity at location 1, because A1 V1 must equal A2 V2. That's why it follows, thus the velocity at 2 is going to be double the velocity at 1. We're also going to have air going through this duct, and so we can know the fluid property of air. Its density is 1.2 kilograms per cubic meter. So let's try and find out what is the velocity at 2 based on this measurement of the deflection. So inside of this tube, conditions are static. So we'll apply Bernoulli's equation on the inside of the nozzle, and we'll use the hydrostatic equation on the inside of this stagnation tube. Okay, so the general principle is that the energy at each of the locations is conserved. Let's look at some of the fluid properties that we know. First of all, the density is 1.2 kilograms per cubic meter. The unit weight, therefore, is going to be 1.2 kilograms per cubic meter multiplied by G, 9.81 meters per second squared. So the unit weight is 11.77 newtons per meter cubed. That is for air. Gamma air, density of air. Also, inside of here is water. So we'll keep in the back of our mind that the density of water, of course, is 1,000 kilograms per cubic meter. And the gamma of water is 9,810 newtons per meter cubed. Okay? And what the principle we're going to apply is that the energy at 1 equals the energy at 2, and energy 2 is equal to energy 3. Therefore, however much energy there is at 1 is equal to the amount of energy at location 3. So we're going to start by calculating how much energy there is at location 1, and we're going to compare it to these other two spots. The three terms of the energy equation, when we apply Bernoulli's equation, the three terms are the pressure head, the elevation head, and the velocity head. So what we're saying is that all of the energy at 1 is equal to all of the energy at 2, and therefore all of the energy here inside of the tube. So location 3 that I'm speaking of here is inside the tube, where the air has stagnated. So let's use the manometer equation and see what it tells us. And so manometer equation tells us that P1 plus gamma, delta H times gamma is equal to P sub T. In other words, the pressure here at location 1, inside the nozzle, since it's a gas, it's air inside the nozzle, what we're going to do, just to simplify things, is we're going to assume that the pressure at the center of that nozzle is the same as the pressure at the top of the water, because air pressure doesn't change very much vertically. And so that's a pretty good approximation, that the pressure at the center of the pipe is the same as the air pressure that's in contact with that water. But then, as we move down through a fluid as dense as water, the pressure changes more rapidly because water has a high density. And so we're saying the pressure at 1 plus delta H times gamma, so some pressure change, and then that gets us to this location, the pressure here, and then we're saying throughout this tube, the pressure is basically constant. There might be some minuscule change in pressure between the top of the tube and the bottom of the tube where it's filled with gas, because maybe they're a few centimeters elevation apart, but for the most part, it's going to be constant air pressure inside that tube, and so any pressures we see are going to be during the change due to the liquid. So that's the manometer equation, and so we can solve for the difference in pressure that's observed. So in other words, if we rearrange this equation, we have P sub t minus P1 is equal to delta H times gamma. And we can calculate that because we have measurements. We see 10 centimeters, so that's 0.10 meters. And the unit weight is water, 9810 newtons per meter cubed. So it's 981 newtons per meter squared. That's how much the pressure changes between 1, which is at the center of the pipe, and on the inside of the tube. That's essentially what this manometer is telling us, is how the pressure changes between 1 and on the inside of the tube. Now, Bernoulli's equation, when we apply it between the 2 points, Bernoulli's equation is saying that the pressure head, elevation head, and velocity head at 1 is equal to the pressure head, elevation head, and velocity head at 2. But we can simplify that because location 1 is at the center line of the pipe, location T is at the center line of the pipe, and so the two elevations are the same. So I'm going to say Z1 equals ZT, because it's the same elevation. And the velocity of the gas inside the tube is 0, because it's a stagnation tube. You know, the air runs into this opening and then it just stops. I mean, when it first hits that opening, it pushes the water up a little bit higher on the left side of that manometer. You know, that's why that deflection is there, is because of the change in pressure, part of it due to the stagnation. You know, we're zoomed in on that stagnation point. You can see these streamlines go around the outside of the stagnation tube, but then there's this one streamline that kind of just stops, and some extra pressure is imparted because of that stagnation there. So we can simplify Bernoulli's equation to be P1 divided by gamma plus V1 squared divided by 2G is equal to P sub t, and then rearrange that, P1 plus density V1 squared divided by 2 is equal to P sub t. I'm sorry, I should have divided this one by gamma. So if we multiply each term by gamma, then we end up with this. And then up above, we found that the change in pressure was 981 newtons per meter squared. So we can rearrange this equation to be, translate that to P sub t minus P1 is equal to density, velocity, 1 squared divided by 2. And so the change in pressure is going to be related to the original velocity at 1. And we could rearrange that to be V1 is 2 times P sub t minus P1 divided by the density and we take the square root of everything. So we're just trying to isolate the variable 1, and then substitute in the constants and the calculated values that we know. So 2 times the change in pressure, which was measured with the manometer, 981 newtons per meter squared, divided by the density. And what we're talking about here is the density of the gas, because in Bernoulli's equation, we're applying Bernoulli's equation inside the nozzle, and inside the nozzle is where the gas is. So we're using 1.2 kilograms per cubic meter, because that's the fluid that Bernoulli's equation is being applied for, to the 1/2 power. So what you get when you crunch all those numbers, it's 40.4 meters per second is velocity at location 1. So let me pause for a moment and bring these up on the screen in case there's anybody who's following along in the recorded video. Yeah. All right, so we have this nozzle, got our fluid constants, and we're saying we know that between these 3 points the energy is conserved. So then what we do is solve the manometer equation to find the change in pressure between point T and point 1. And we can substitute in this equation where we've just rearranged Bernoulli's equation to solve for the unknown velocity at 1. If you have some change in pressure, you know that it's partly caused by the velocity at 1. And then in the problem statement, it said that the velocity at 2 is going to be double the velocity at 1. Now, here it says, thus, V2 is twice V1. So then, from that, we know V2 is 80.8 meters per second. So this first example is really simple. The second example is a little bit more complicated because we're combining two ideas together. We're combining Bernoulli's equation and the manometer equation together. And for the rest of the semester, it's kind of going to be that same thing where what makes problems complicated isn't like the underlying fluid mechanics principles, but it's just because we're combining two different ideas together. Like we'll be combining Euler's equation along with like trying to calculate the forces that occur when you are accelerating a fluid. Or in this case, we'll be combining the manometer equation, which is how we measure the pressure change, along with Bernoulli's equation, which relates the pressure change to a velocity change. Okay, well, that's all I have for you today. Please remember that on Tuesday of next week we won't meet, so I'll be looking for an email from me that has the details of that recorded lecture, and your homework assignment is due on Tuesday. All right, have a good day.